Hi, I'm Jongbin An, a master's student studying at Yonsei University, Seoul, South Korea. The paper I'm going to present is called MiniROAD, Minimal RNN Framework for Online Action Detection. Our research focuses on online video understanding, where frames are provided sequentially in a streaming manner. The objectives of online action detection and action anticipation are to predict the actions in the current or upcoming frames, using only the past and present data. A transformer is among the most prevalent architectures in recent computer vision tasks due to its exceptional ability to capture long-term dependencies. However, the computational complexity of its attention mechanism scales quadratically with sequence lengths, limiting its utility in scenarios where efficiency is paramount, such as real-time online tasks. In contrast, while RNNs have linear computational complexity relative to sequence lengths, they often struggle to capture long-term dependencies effectively. As a result, transformer variants dominate these tasks. Notably, the most effective version incorporates a two-stage memory compression architecture capable of handling sequences up to 512 seconds with a distinctive long-term memory. The precise extent of temporal information required for online video tasks remains a matter of debate. To shed light on what specific elements transformer variants focus on, we visualize the attention heat map of transformer encoders in OADTR, the pioneering effort to integrate transformers into online action detection. The heat map reveals a predominant focus on the most recent frames and their immediate neighbors, suggesting that the extensive long-term information might not be essential for these tasks. This naturally leads to the question, why have RNNs been performing so poorly? Our study illustrates that when trained optimally, a simple RNN can not only achieve impressive performance, but also bring about substantial improvement in efficiency. We attribute the suboptimal performance of RNNs to a training inference discrepancy. The prevalent training practice for many video tasks involves segmenting the video into multiple clips and utilizing these clips for batch-wise training. This unwittingly creates a discrepancy between training and inference. During inference, the model has access to the entire video, whereas in training, it only sees isolated clips with no contextual linkage between them. This discrepancy is crucial because RNNs deeply depend on prior hidden states. In essence, while most inference predictions draw upon extensive temporal information, RNNs have been unintentionally trained using predictions with limited temporal context. To alleviate this discrepancy, we have adopted a very simple yet effective strategy. We observed that the traditional loss function has unwittingly applied uniform weights across all time steps. Conceptually, this uniform weight can be rewritten as the one in the middle, where alpha t represents the weight of the loss at time t. To align our training with the typical inference scenario, where predictions draw heavily on a broad span of temporal information, we explore different weight assignment strategies. The uniform weight represents the standard approach. Linear and exponential depict weights that increase linearly or exponentially, respectively. In the learnable weight approach, we treated alpha t at each time step as learnable embeddings. Lastly, the step function assigns weight predominantly at the end of the time step. Of all these, the step function proved the most effective in bridging the gap between training and inference. Through this simple methodology, our very simple RNN-based model was able to achieve state-of-the-art in Thomas, TV series, and fine action. The model's efficiency is particularly noteworthy. It operates approximately 200 times faster than previous models. However, this isn't the ultimate speed, as we must also factor in the time required for optical flow computation and the extraction of both RGB and optical flow features. When accounting for all these processes, the speed is represented as the overall FPS. A remarkable improvement in this overall FPS was observed when using the faster NVIDIA optical flow algorithm. We also tested action anticipation on Salma's dataset and showed that it was also effective in action anticipation. The most intuitive solution to address the training and inference discrepancy is to utilize the entire video during training. We implemented this approach using a batch size of 1 and the full video, observing a substantial boost in performance. Our proposed non-uniform weight method closely approximates the results achieved by using the entire video. Moreover, our method offers added benefits such as batch-wise training and reduced memory consumption. Our paper code can be found on our project page, so please check them out. Thank you for listening.